So we study refraction of light through a prism. We shall take an example of a triangular prism. The triangular prism is a three-dimensional structure which might be represented in this form. So actually you can say that prism is actually a portion of a transparent medium bounded by two plane surfaces which are inclined to each other. So a prism is basically a portion of a transparent medium, bounded by two refracting surfaces, and the refracting surfaces are inclined at some angle. Refracting surfaces. Now these refracting surfaces are inclined at some angle, and that angle is called as the angle of the prism. So as per this example, you can see that this ABED, in this example, ABED and ADCF, these are the refracting surfaces. Now these refracting surfaces are inclined to each other at some angle, and that angle is called as the angle of the prism. So because this is a three-dimensional structure, so you can see that this angle is the angle of the prism, or this angle is the angle of the prism. So the edges are inclined at some angle, and this is angle A, or simply you can say, as per this diagram, angle BSC. This is the refracting angle of the prism. Refracting angle. And the line of intersection of these refracting surfaces is called as the refracting edge. The line of intersection of the refracting surfaces is called as the refracting edge. So these two surfaces, they meet at a line that is AD. That means ABED and ADFC or ADCF, they meet, and this is the line of intersection. So AD, that is called as the refracting edge. So a transparent medium bounded by two refracting surfaces. These refracting surfaces are the surfaces through which light will refract, and they meet at a straight line. That straight line is called as the refracting edge, and the angle of inclination between the refracting surfaces is called as the refracting angle or the angle of the prism. This is also called as the angle of the prism. So that means that light will enter through this surface, that is ABED or ADCF, and pass through the other surface. So light enters this surface and passes through this surface. And the base of the prism is obviously BC. The prism is BEFC. FC is the base of the prism. So the prism will sit on its base, and that's why it is called as the base of the prism. So apart from these surfaces, apart from the refracting surfaces, the other surfaces are more or less, you can say, they are translucent. Light will not refract through those surfaces. That means light will not refract through ABC, light will not refract through DEF, and light will not refract through BCFE. So this section through which the light actually refracts, we can project that and get a triangular section of the prism, and that's why it is called as the triangular prism. This is also called as the principal section of the prism. So you can say that the portion of the prism or the section of the prism which is perpendicular to the refracting edge is the principal section of the prism. The section of the prism which is perpendicular to the refracting edge perpendicular to the refracting edge. That is called as the principal section of the prism. Section of the prism. So in this triangle you can say that this triangle ABC is the principal section of the prism. So whenever we study refraction through a prism, we will study the refraction through the principal section of the prism. It is better to say that ADFC is the refracting surface. So this is a triangular prism because the principal section is a triangle. The principal section can be a pentagon, the principal section can be a hexagon, and in those situations it will be called as a pentagonal prism or a hexagonal prism and so on. So let us study the refraction through the prism, and we will take the principal section only. So suppose this is the principal section of the prism, the triangle ABC, and this is the angle of the prism, that is the angle A. Suppose a ray of light is incident on AB. At this point of incidence, we will draw a normal on AB. And let us extend the normal. Light will definitely bend towards the normal because light is entering from rarer to denser medium. It will bend toward the normal. Now this is the point of incidence on the surface AC. So again we have to draw a normal at that point. Let these two normals or perpendiculars meet at some point. And now you see that light passes from denser to the rarer medium, and so it will bend away from the normal. So this is the incident ray, this is the ray through the prism, and this is the emergent ray. Let me name the points. This point is suppose point M. This point is suppose point N. This point is suppose point P. Now, if I produce the incident ray in the forward direction, and if I produce the emergent ray in the backward direction, then they will meet at some point. The angle made by the incident ray produced forward and the emergent ray produced backward, that angle is called as the angle of deviation. This angle is called as the angle of deviation, delta. Let me name this point as Q. So now, angle between the incident ray and normal is the angle of incidence I1 on the first surface ABC. This is the angle of refraction R1, and this is the angle of incidence on the second surface. Let me call that as R2, and the angle of emergence let me call as I2. So we can definitely have a relationship between I1, R1, R2, I2 delta and the angle of the prism. Now instead of writing angle A, or we will write simply A as the angle of the prism. Angle of the prism. Though A represents the vertex, but sometimes we write A and that represents the angle of the prism. So now, if you observe the diagram, we can easily find the relationship between I1, R1, I2, R2 and A and delta using the principles of geometry. So in this triangle, if you observe your angle QMN, that is equal to I1 minus R1, because this is the incident ray produced in this direction and this is the normal. So this I1 is vertically opposite to this one totally. So this angle, that is angle QMN, is I1 minus R1. Similarly, angle QNM, that is this angle QNM is equal to I2 minus R2, because I2 is vertically opposite to this entire angle. So I2 minus R2 will give you this angle, that is QNM, I2 minus R2. So in triangle QMN, the exterior angle is the sum of interior opposite angle. Now the exterior angle is delta, and that is equal to this angle plus this angle. So your delta or the exterior angle is angle QMN plus angle QNM. So what you get is delta equal to I1 minus R1 plus I2 minus R2, which means that your delta is I1 plus I2. If I take minus common, that is minus of R1 plus R2. Now, in triangle AMN, you know that the angles, sum of the angles of a triangle is 100 degree. So angle A plus angle AMN plus angle ANM is equal to 180 degree. Now, what is angle AMN? Now, because this is perpendicular, this is 90 degree. So this total angle is 90 degree. AMP is 90 degree. So AMP is 90. So 90 minus R1 will give you AMN. So this is 90 minus R1. Similarly, this is the normal or perpendicular. So ANP, this entire angle is 90 degree. So angle ANM is 90 minus R2. 90 minus R2. And that is totally 100 degree. So you see that 90 plus 90 is 180 and 180 will cancel each other. So what we get is angle A, or the angle of the prism, is R1 plus R2. Or simply we can write A is R1 plus R2. As I have said that the angle A or the point A both represents the angle of the prism. Now using this one and this one, delta is I1 plus I2 minus R1 plus R2. So instead of R1 plus R2 you can write A. So therefore you see that this delta is equal to I1 plus I2 minus A. Or you can say that delta plus A is equal to I1 plus I2. These are two important relationships in a triangular prism. Delta plus A is equal to I1 plus I2. So let us now look at the factors that affect the angle of deviation in the prism. So the angle of deviation depends on four factors. You can say the deviation or the angle of deviation, it depends upon angle of incidence, so the behavior of deviation delta with the angle of incidence I can be done by an experiment, though we don't have that experiment in the syllabus, but still we will study it from a very qualitative point of view. Now the angle of deviation also depends on the material of the prism. That means it depends on the refractive index, you can say, material of the prism. If the refractive index of the prism is mu, then the angle of deviation depends on the refractive index of the mu. It depends on the angle of the prism, and it depends on the wavelength or the color of light has been used. We have assumed that, as we have already seen, that how refraction occurs using polychromatic and monochromatic ray, but unless specified, A single ray, whenever we take, we consider it to be monochromatic. So in this case, in the prism that I have analyzed the deviation, I have taken a monochromatic beam or a monochromatic ray. That's why I am saying that it is dependent on color or wavelength lambda. So there are the four factors on which angle of deviation depends. So if you say it depends on the material of the prism, then it has been found experimentally that for a given angle of incidence, the prism with higher refractive index will produce a greater deviation. So if you consider this one, material of the prism, I will come back to the first point later, but if you say that how it depends on the material of the prism, you might have observed when I discussed deviation using polychromatic light. In the similar manner, you can say that if the refractive index is greater, then the deviation is also greater. That means generally prisms are made up of crown glass or flint glass, and flint glass has a higher refractive index. And you can remember this, that flint glass refractive index of flint glass is greater than refractive index of crown glass. These are the two special type of glasses that are used to construct prism. And generally, refractive index of flint glass is greater than refractive index of crown glass. So higher the refractive index, more will be the deviation. Higher the refractive index, more will be the deviation. And with respect to angular prism, if the angle of prism increases, then the deviation also increases. So deviation increases with increase in angle of the prism, deviation increases with increase in the refractive index of the material of the prism. Now, you know that the refractive index is different for different colors, and that refractive index decreases with increasing wavelength. So you can say that the refractive index of the material of the prism is maximum for violet and minimum for violet, and it's minimum for red. So you can say that the deviation is maximum for violet and it is minimum for red. That I have already described in the previous video, refraction 1. And wavelength of red is greater than wavelength of violet. So the dependence on color is such that if the refractive index increases, then the deviation increases, and if the wavelength increases, then the deviation decreases. So a prism will deviate more amount of violet light than red light. The red light will be least deviated, whereas the red light has greater wavelength and violet has the least wavelength. Now let us come back to the first point, angle of incidence. The variation of the angle of incidence with the angle of deviation can be studied only experimentally. So after conducting several experiments, it has been realized that if the angle of incidence initially increases, then the deviation decreases. It becomes minimum at some specific angle of incidence. Then if the angle of incidence further increases, the angle of deviation also increases. I repeat, initially if the angle of incidence increases, then the angle of deviation decreases. It becomes minimum at some particular angle of incidence. Then if the angle of incidence increases further, the angle of deviation also increases, and that can be understood using a graph. So suppose there is a graph which has been plotted after conducting several experiments using different angles of incidence and measuring the different angle of deviation. If we plot deviation along the y-axis and the corresponding values of angle of incidence along the x-axis, then initially with increase in angle of incidence, the angle of deviation decreases. It becomes minimum at some point, at some angle of incidence, this deviation is minimum, and then if angle of incidence further increases, the deviation increases. So the graph is somewhat like this, and this particular angle of deviation, which is the minimum value, can be denoted as delta m. Now, if you conduct experiment and if you achieve the particular angle of incidence at which the angle of deviation becomes minimum, then you will realize that if the prism is mounted in such a manner that the deviation is minimum, then the ray of light that passes through the prism will become parallel to the base of the prism. And this is true for equilateral triangle. Suppose we consider a equilateral prism, that means the principal section of the prism is actually an equilateral triangle. That's why I am saying it is as an equilateral triangle. The refracted ray inside the prism will travel parallel to the base of the prism. And when the deviation is minimum, then the angle of incidence is equal to the angle of emergence. That means I1 is equal to I2, and so R1 will be also equal to R2. And the straight line that I had drawn previously within the prism, that was slightly inclined to the base, that straight line or that ray within the prism will travel parallel to the base of the prism. So this is what will happen when the deviation is equal to the minimum value. Then I1 will become equal to I2 and R1 will become equal to R2, and let R1 and R2 be called as R, suppose. So A, which was R1 plus R2, will become 2R, that is, you will get A as 2R, and if you remember, I1 plus I2 is equal to A plus delta. Now if the minimum deviation occurs, then this delta is delta m, and I1 and I2, suppose both I1 and I2 are now denoted by I, because they are always equal when deviation is minimum. So this can be written as 2I equal to A plus delta m, and so the angle of minimum deviation will become 2I minus A, twice the angle of incidence minus the angle of the prism. So suppose you are using a equilateral prism, obviously your A will be 60 degree, and suppose the angle of incidence is 45 degree at which the deviation becomes minimum. So twice into 48 minus 60, that is 36, will be the angle of minimum deviation. So this is the realization when angle of deviation is minimum, and as I have already said that the ray inside the prism, ray within the prism, will travel parallel to the base of the prism. Base of the prism, provided your deviation is minimum. So these are the four factors on which the angle of deviation depends. It depends on the angle of incidence I, it depends on the refractive index of the material of the prism, it depends on the angle of the prism, and it depends on the wavelength of light used. So equilateral triangle is just a special case, but the ray will always travel parallel to the base of the prism. If you remember the diagram that I used to find the relationship between I1, I2, A, delta M, delta. In that case, the diagram was something like this. The ray was shown to be inclined at some angle to the base. Now, this ray, which was inclined, will become parallel when the deviation is minimum. So this ray, suppose let me call it as PQ and the base is BC. Then when the deviation is minimum, the ray inside will become parallel to the base of the prism. That means at minimum deviation, this PQ will become parallel to the base of the prism. This is what will occur when the prism has been mounted so that the deviation becomes minimum. At every position, the deviation cannot become minimum. The deviation becomes minimum at some specific value of the angle of incidence. So it has to be mounted in some specific way, then only it is possible. It is a common observation that if an object is placed in a denser medium and is viewed from the rarer medium, its depth appears to be less than its actual depth. And this is based on the principle of refraction of light. So, if an object kept in denser medium is viewed or observed from the rarer medium, the depth of the object appears to be less than the actual depth. Its depth appears less than the actual depth of the object. The actual depth is called as the real depth, and the depth that appears, which is less than the actual depth, is called as the apparent depth. So, a very common example you can take, suppose you drop a coin in a glass tumbler and then you pour some water into the glass tumbler, and then if you view the glass tumbler from vertically downwards, if you view the glass tumbler in a vertically downward direction, you will realize that the depth of the coin within the glass tumbler has decreased. It appears that the coin has raised some distance above its actual position. So that is what we can realize or analyze from the refraction of light. So an object placed in a denser medium, when viewed from a rarer medium, appears to be at a depth which is less than its real depth. So let us consider an example and analyze it. Suppose this is a vessel and it contains some liquid. The liquid is of a refractive index greater than the surrounding medium. The surrounding medium is suppose air, which is the rarer medium, and its refractive index is suppose mu A. And the refractive index of the liquid or any transparent medium is suppose mu. Actually, we have placed a very small coin or a pebble. Suppose it is taken in the shape of a point. A coin or a stone has been dropped and liquid has been filled up to some height. And this coin is viewed in the vertically downward direction. You place your eye above the level of the water or level of the liquid, and if you view it, then it appears that the coin has raised to some position above its actual level. It appears to be raised some different point above the actual level. So suppose this is the position of the coin. Let me call this position as position O. So let us consider a ray of light that falls on the surface perpendicularly, and the perpendicular ray will definitely not deviate. Let us consider another ray of light that falls at some angle, and if you draw the perpendicular at this point of incidence, you will see that the ray will bend away from the normal. Suppose it will bend away in this direction. Because the ray of light is moving from denser to rarer medium, it will bend away from the normal. If I produce this ray backwards, you can see that when anyone is viewing along this direction, it means that this object appears to be raised to this point. Suppose this point is called as I. Suppose this point is called P, then your Pi will be the apparent depth and Po will be the actual depth of the object. This angle is angle of incidence I. This is also angle of incidence I, because this is also perpendicular and this is the normal which is also perpendicular. They are mutually parallel and this is the angle of incidence. So these are alternate angles and this is also I. This is angle R, because the refracted ray has been produced backwards. Refracted ray has been produced backwards. So this is a straight line, and so this angle is also angle R, because they are corresponding angles. Let me call this point M. Now within the field of view of the person, P and M are sufficiently close. So let me use Snell's law, and from Snell's law I can say sin I by sin R is equal to refractive index of the second medium with respect to first medium. So suppose this is a medium, either it is some liquid or something like that. Let me call the refractive index as mu m, refractive index of the denser medium. So this will be refractive index of air with respect to the denser medium. That is refractive index of air by refractive index of the medium. So refractive index of second medium with respect to first medium will be written in this manner. So in this triangle OPM, in triangle OPM, if I apply trigonometry and find sin I, what I will get is sin I is Pm by OM. And in triangle PIM, if I apply trigonometry to find sin R, I will get Pm by Im. So therefore, sin I by sin R will give you is equal to Pm by OM divided by Pm by Im, which will become Im by OM. Since within the field of view of the person, P and M are very close. Since point P, M are very close, Im is very nearly Pm, IP, and OM is very nearly OP. So therefore, you can say that sin I by sin R is equal to IP by OP. Now, we have already determined what is sin I by sin R. So, you can now say that sin I by sin R is refractive index of air with respect to the medium, that is equal to your IP by OP. Okay. Now, you can say that OP by IP is equal to refractive index of the medium with respect to air, because you know that 1 by A m mu A is actually A mu m. By the principle of reversibility of light, we have already proved it. if I drop the subscript m and write mu, and refractive index of air, if it is taken to be 1, then this becomes mu m by mu a, that is mu by 1. So what I get is OP, which is the actual depth or the real depth, by IP, which is the apparent depth, is equal to refractive index of the denser medium, that is mu. So this becomes the refractive index of the denser medium. I hope you have copied it. And now OI will be called as the apparent shift. That means it appears that the object at the position O has raised by the distance OI and has reached this point I. So OI will be called as the apparent shift, or the shift simply. So this apparent shift or shift, which is OI, is actually OP minus IP. And now the shift I can be written as, if I take OP common, I can write 1 minus IP by OP. Now OI, or the shift, is equal to OP. What is OP? OP is the real depth. So the real depth into 1 minus OP by IP is mu. OP by IP is mu. So IP by OP is 1 by mu. So you can say that the apparent shift or shift is real depth into 1 minus 1 by refractive index of the denser medium, provided the rarer medium is air of refractive index 1. Example of the real depth and apparent depth problem. Suppose it is given that a postage stamp is kept below a rectangular glass block of refractive index 1.5, and when it is viewed from vertically above, it appears to be raised by 7 mm. You have to find the thickness of the glass block. So the refractive index is given and the apparent shift is given. So shift, as you all know, it is real depth into 1 minus 1 by mu. Now what is real depth here? In this case, or in this problem, the real depth is actually the thickness of the glass block. So here, thickness of the glass block is suppose x, and that is equal to your real depth. If the thickness I have assumed as x, and that is actually the real depth. The shift is 7 mm. Real depth is x into 1 minus 1 by 1.5, because the refractive index is 1.5. So 7 equal to x into 1.5 minus 1 is 0.5 by 1.5. That is obviously point will shift. 5 by 15 is 1 by 3. So x you will get 21 mm. So the thickness of the glass block is 21 mm.